My name is Jongsomjit. I am the co-chairman of the section. So the cobalt story continues, and the next paper, cobalt for compound formation in cobalt-based catalysis. Jongsomjit and I start again. And the premium is that I have a chance to pronounce this name, the name of the author the second time. So the name of the author is Jongsomjit and Jongsomjit. And the title of the paper, Cobalt-supported compound formation in cobalt-based catalysis.
Okay, thank you. Good afternoon, everybody. Today I'm going to talk about cobalt-supported compound formation in cobalt-based catalysis. Basically, supported cobalt catalysts are the preferred catalysts for physical synthesis or FTS based on natural gas because of their high activity for FTS, high selectivity to linear hydrocarbons, and low activity for water gas shift reaction. However, the formation of cobalt and the support can occur under pretreatment and under reaction conditions, leading to the catalyst deactivation. Since it is known that water vapor is a byproduct of metal catalyst reaction, and from the previous work in our group, it was found that water vapor has a major impact on alumina-supported cobalt catalyst by increasing the amount of non-reducible cobalt aluminate formed during standard reduction and TPR, resulting in a lower reducibility of the catalyst. In a laboratory, the amount of water vapor can be minimized. However, during reduction of the catalyst on an industrial scale, this is more difficult. Otherwise, it is uneconomic to physically remove all the water from the process. In order to stabilize the catalyst activity, the amount of cobalt support compound formation must be minimized. However, before we can do that, it is very important to first fully understand the nature of cobalt support compound formation and how this formation affects the characteristic of the catalyst, and then what we are trying to do is to develop a strategy to minimize the amount of cobalt support compound formation in order to improve the catalyst activity. Therefore, the objective of this study were to develop a better understanding of cobalt support compound formation under different reduction conditions, and to identify cobalt support compound formation using different characterization techniques, and also to investigate the effect of ruthenium promotion on cobalt support compound formation also. Actually, there are two types of cobalt catalysts in this study prepared by the incident wetness impregnation. Cobalt on gamma alumina with 20% by weight of cobalt, and cobalt promoted with ruthenium with 20% by weight of cobalt also, and 0.5% by weight of ruthenium. After calcination in air at 300 degrees Celsius for 2 hours, the catalyst samples were reduced in hydrogen at 350 degrees Celsius for 10 hours into different conditions with and without the additional water vapor during reduction and then passivated. So we have the catalyst nomenclature. Where C refers to the calcite catalyst samples, RP refers to the reduced and passivated catalyst sample, and RWP refers to the reduced with the addition of water vapor during reduction and then passivated catalyst samples. After pretreatment, all catalyst samples were characterized using different characterization techniques as mentioned there. Hydrogen chemisorption was performed to determine the number of reduced surface cobalt metal. This is related to the overall activity of the catalyst during FTS. And from this table, we can see that the overall cobalt dispersion increases with ruthenium promotion and decreases with the additional water vapor during reduction. It is suggested that ruthenium promotion can facilitate the dispersion of cobalt metal. TBR is one of the most powerful characterization techniques used to identify cobalt support compound formation present. It is performed to determine the reduction behavior and to measure the reducibility of the catalyst sample after various pretreatment conditions used in this study. And these are TBR profiles of about cobalt-304, the cobalt catalyst, and the cobalt ruthenium catalyst after various pretreatment conditions. Basically, two steps of reduction can be seen except for the calcite cobalt catalyst, which have three-step reduction. The first step at the lower temperature is assigned to the reaction of cobalt-304 to cobalt oxide and cobalt oxide to cobalt metal. And the second step at higher temperature is assigned to the reaction of cobalt species strongly interacting with the support to cobalt metal. However, three steps of reduction can be seen for the calcite cobalt catalyst, where the first step here is just the reduction of smaller particles of cobalt oxide or highly dispersed cobalt 304 to cobalt oxide and cobalt metal. From TBR, we can see that ruthenium promotion can facilitate the reduction process by lowering the reduction temperature, whereas water vapor here inhibits the reduction process, resulting in a shift of the second peak to higher temperature. And from TBR profiles, the amount of hydrogen consumption is related to the integration of area peak below curve. When the amount of hydrogen consumption is known, the reusability of the catalyst sample can be calculated, and the result is shown on the next slide. And these are the reducibility of the catalyst sample during TBR after various pretreatment conditions. This is the reducibility of the catalyst during TBR at 30 degrees Celsius to 900 degrees Celsius. And this is the reducibility of the catalyst sample at 30 degrees Celsius to 400 degrees Celsius, which is related to or comparable to the reducibility of the catalyst during standard reduction. We can see that the reducibility of the catalyst sample decreases with the additional water vapor during reduction and increases with ruthenium promotion. Considering the reducibility of the catalyst sample at standard reduction, we can see that only 60% of cobalt species can be reduced. That means about maybe 40% is not reducible cobalt species. These cobalt species can be assigned to the cobalt species strongly interacting with the support, or just we can define it as cobalt quartz aluminate here. From TBR, it can be seen that cobalt support compound formation was formed during standard reduction and TBR, and this compound formation causes a decrease in the reducibility of the catalyst samples. And besides TBR, the main objective of this study is to use different characterization techniques to identify cobalt support compound formation. And this is the result from the other techniques that we use to identify cobalt support compound formation. DET surface area was performed to determine if the total surface area of the catalyst changed after different pretreatment conditions used in this study. And from this table, we can see that the total surface area of the catalyst samples after various pretreatment was, were just slightly less than that of the support. That means there is no significant change in the total surface area of the catalyst samples after various pretreatment conditions used in this study. XRD was performed to determine the crystalline phases of cobalt catalyst after various pretreatment conditions. This is the XRD panels for the calcite, cobalt, and cobalt ruthenium, the reduced and passivated catalyst sample, and the reduced with the additional water vapor during reduction and passivated catalyst sample. For references, the XRD panels for the alumina support, cobalt oxide, cobalt-304 spinel, cobalt aluminum spinel were also carried out. It can be seen that the XRD panels for gamma alumina was present in our catalyst samples. And compare the XRDs of the catalyst sample with the references, we can see that after calcination, cobalt-304 was present in the calcite catalyst sample, was in cobalt, ruthenium, and cobalt catalyst. No piece of ruthenium were detected in our cobalt catalyst sample, cobalt ruthenium catalyst sample. And after reduction, cobalt-304 was reduced to cobalt oxide and cobalt metal. Cobalt oxide P can be seen here. And cobalt metal P cannot be seen due to the overlap with those for gamma alumina. No piece of cobalt aluminum spinel were detected, and that means cobalt aluminum probably form is just highly dispersed. However, Raman spectroscopy gives more useful information about cobalt aluminum formation. And these are Raman spectra of the cobalt and cobalt ruthenium catalyst, the calcite sample, the reduced and passivated catalyst sample, and the reduced with the additional water vapor and passivated catalyst sample. Again, for references, Raman spectra of cobalt oxide, cobalt-304, cobalt aluminum spinel were also carried out here. And as the result from XRD, after calcination, cobalt-304 was present in the calcite cobalt catalyst, both in cobalt and cobalt ruthenium catalyst. And after reduction, cobalt-304 was reduced to cobalt oxide and cobalt metal, which can be seen by Raman spectroscopy. However, in strain, the broad Raman band between 400 to 750 were seen, and this peak, the peak area is just depends on the catalyst composition and the pretreatment conditions as well. So we just try to focus on these reactions. We can see that the peak area increases with the additional water vapor during reduction and decreases with the ruthenium promotion. And we know from TPR results that the amount of cobalt support compound formation was also increases with the additional water vapor during reduction and decreases with ruthenium promotion. So these Raman bands can be assigned to the cobalt aluminate formation with occur probably due to cobalt ion migration into alumina matrix and from surface non-stoichiometric cobalt aluminate formation. And this SEM gives the information about the morphologies of the catalyst after various pretreatment used in this study. And these are SEM micrographs of the calcite, cobalt, and cobalt ruthenium catalyst on the surface of carbon tape used as a sample holder. From these micrographs, we can see no differences in morphologies of the catalyst samples. However, with higher magnification on the individual catalyst granule, we can see the difference in cobalt dispersion here. And these are, again, SEM micrographs of the individual catalyst particle, the calcite cobalt and cobalt ruthenium catalyst, the reduced and passivated cobalt and cobalt ruthenium catalyst also. The white or light spot here represent high concentration of cobalt and its compound, and the darker area represent the alumina support with minimal or no cobalt present. And from these micrographs, we can see the difference in dispersion of cobalt. We can see that with ruthenium promotion, cobalt is more dispersed, resulting in the observation of smaller cobalt all over the catalyst surface, or we can call this one is just cobalt patches, smaller cobalt patches all over the catalyst surface. And this will be better described also using the result from hydrogen chemisorption is shown here. With ruthenium promotion, the overall cobalt dispersion is much more higher. That means it's more dispersion here. And this is probably the most dramatic change in SEM micrographs of the reduced and passivated cobalt catalyst with and without the additional water vapor during reduction. Again, the white or light spot here represent cobalt patches, and the darker area represent the aluminum surface with minimal or no cobalt present. We can see that there was the greater number of smaller cobalt patches in the reduced and passivated cobalt catalyst sample without the additional water vapor than that with the additional water vapor. At this point, maybe there are two possibilities. Either water vapor can facilitate the agglomeration of smaller cobalt patches and form larger cobalt patches, or cobalt ion form smaller cobalt patches. Water vapor may increase the diffusion of cobalt from the smaller cobalt patches into aluminum matrix and form cobalt aluminum. Maybe both phenomena probably occur with the latter is more important and resulting in a significant cobalt support compound formation. So at this point, it can be concluded that water vapor has an impact on alumina-supported cobalt catalyst by increasing the amount of non-reducible cobalt aluminate formed during standard reduction in TPR, resulting in a lower reducibility of the catalyst. Water vapor probably increased the migration of cobalt ion into alumina matrix and form cobalt aluminate. And the cobalt aluminate form is different from cobalt aluminate spinel, and probably it is like a highly dispersed cobalt aluminate with deficiency of cobalt species present. And highly dispersed cobalt appears to be more likely to form cobalt aluminate. And ruthenium promoter can decrease the impact of water vapor on cobalt aluminate formation. And finally, I would like to thank the Royal Thai government for the financial support and the Energy International Incorporation for providing some catalysts used in this study. And thank you for your attention. I would be happy to answer any questions.
Thank you for the presentation. So we have time for discussion. Several decades ago, we studied the formation of spinel between different oxides, and it really required a high temperature. And I have a feeling that you found spinel formation at a relatively low temperature. What was the temperature of the solid state reaction in your case?
The reaction is 350 degrees Celsius.
And you assume that the spinel formation, or so-called spinel formation, proceeds between the reduced cobalt and the alumina, or the unreduced cobalt oxide and the alumina. So the reaction proceeds or occurs between the unreduced cobalt oxide and alumina, or between the cobalt metal and alumina.
I think problem with is its cobalt ion. I mean, not cobalt metal, just cobalt oxide. Because it has to be migrated into aluminum and nickel for cobalt.
This kind of cobalt oxide on the surface you define as a non-stoichiometric or whatever.
That's very cobalt.
Can it be assigned? Yeah. Can it be assigned to the so-called cobalt surface phase, which was first, I think, discovered by Hercules and co-workers, and we proved it, in 1990s, physical chemistry papers, which has a monolayer of cobalt oxide on the surface. This is not a surface spinel, but it's a cobalt oxide surface, which is very hard to reduce. It's simply impossible to reduce, even in presence of platinum, for instance.
I think it's the same thing.
This is similar thing, but you...
Yeah, highly dispersed cobalt with cobalt efficiency. So it doesn't form like a cobalt aluminum spin. We can see what they have to O4 something like that.
So in fact, this answer to Professor Sarnoshi's question contains some cobalt ions, cobalt 2+.
Yeah, cobalt 2+. Yeah, like a migration into aluminum matrix.
You know that there was a famous German scientist, his name was Hüttig. Hüttig studied the solid-state reaction before the Second World War, and he assumed that the solid-state reaction consists of 6 phases. And before the real spinel formation, he observed a so-called Zwischenzustände, a transitional state, which exhibited a very high activity in several reactions. So you might have such a type of disordered state. It is not a complete spinel, but it is not only the single oxide, so it is a mixture or between the spinel and the oxide. So maybe this is a transitional state of the reaction. You did not have a complete spinel. I guess that these catalysts, these solids, might exhibit a high catalytic activity in some cases, as found